Thanks to Yuvraj and Pranoy for setting the stage for my talk. So now everyone is convinced that why should we use SCMs, right? Supplementary cementitious materials. And we look for few properties, right? Which include consistency, for an example. But as you can imagine, we have a lot of material which doesn't have consistency, right? A lot of undesirable stuff is in those wastes, for an example. So in this talk, basically what I will try to address is how do we use these wastes? How do we characterize those? And I will show you some of our previous work on utilization of Indian biomass ash. So the presentation outline, what I will talk primarily is on agricultural wastes, which are very important from India's perspective, as we'll see later. So I will talk about rice husk ash, sugarcane bagasse ash, and mixed rice husk sugarcane bagasse mixed ash. Okay. And I will then come to a case study on application of Indian biomass ash in brick masonry. And I will conclude with the challenges with high volume utilization of these agricultural waste. So let's look at some of the statistics. So bioenergy, which is derived from biomass, is the largest renewable energy source globally. It accounts for roughly 13% of world's total energy consumption. Okay. For more details, please go through this report by Global Bioenergy Statistics to 2019. And bioenergy accounts for roughly 70% of the renewable energy consumption. And agricultural residues offer one of the most promising sectors of growth in bioenergy generation, right? And according to an estimate, we have roughly 4 to 9 billion tons of these residues, which can be used for energy purpose, right? So if you look at the energy which we can get from these agricultural residues, basically it can potentially meet 3 to 14% of total energy supply globally. Let's look at Indian perspective. So biomass is an important energy source for India. It's renewable, widely available. And if you look at the availability around India, we have roughly around 500 million metric tons of biomass. And roughly 1/3 of total primary energy is derived from biomass. Okay. And recently, Ministry of New and Renewable Energy has initiated this program on biomass power and cogeneration program, basically with the objective of promoting technologies of optimum use of biomass resources for grid power generation. So there's a lot of potential in this biomass, right? And agricultural residue is part of that biomass. So how do we use that? That will be the focus of this. Also, you see sometimes cases of uncontrolled burning, right? Which leads to air pollution in a lot of parts of country, right? So this is due to uncontrolled burning of crop residues. And we know that this agricultural waste has potential to be used as fuel for power generation. So pollution control industrialized facilities can offer a solution for uncontrolled burning. Rather than going for this uncontrolled way of burning, burning can be controlled and we can harness energy, right? And other things. So typically, if you look at small and medium sized industry in India, whether it is sugar industry or paper industry, so they use a lot of materials or agricultural waste to get energy, right? This is just one example of a paper industry where they use pet coke or coal with other agricultural waste. Could be bagasse, rice husk, wood chips. Again, it's very important to understand that they don't use the same raw material every time. It depends on the seasons, like availability. That's why it's very important to pay attention to the raw material they use for the energy generation, because that will have implication, as we'll discuss later. And typically, because these agricultural waste have a calorific value, right? Maybe not to the level of coal, but roughly 50% calorific value you can get from bagasse and rice husk, right? So that's the reason why they are used to get energy. And they are roughly, boilers are at 700 to 800 degrees centigrade temperature, and you get energy out of it. So in this again, the agricultural waste of interest are these rice husk ash, sugarcane bagasse ash, and mixed. Right. Sometimes industries tend to use the mixed raw feed, right? And in that process, what happens? You generate a lot of ash. How do we use that ash? Okay. So first, I would just go over a few earlier studies. So for an example, if you look at the rice husk ash, it's very highly pozzolanic material, as now you can understand. And Professor P.K. Mehta, late Professor P.K. Mehta, did one of the earliest works on the utilization of rice husk ash. So this is just the data from the work he did in late 70s, right? Where you can see like what happens when you add rice husk ash with lime, right? So you can see that you can get significant strength, right? In left table, let me just use the pointer. So yeah, in the left table, you can see that if you use 80% of ash with 20% of lime, right, at 0.5 water cement ratio, the mortar cube strength after 28 days was around 35 MPa. So you can get decent strength just by combining rice husk ash with lime, right? So again, this is because of the high pozzolanic reactivity of rice husk ash, right? And on the right table, you can see what happens when we start substituting, right? Substituting cement, right? So with 30%, 20% replacement of cement, the strength is roughly around 61 megapascal, right? Where when you use the plain cement, you had strength of 43 megapascal. Again, these are the results from Professor Mehta's study from late. Significant work has been done. Now we have very good understanding of this material, why it is very highly pozzolanic, right? It's because of it's a high degree of amorphousness. Suppose you do X-ray diffraction of this material, you will see a broad hump, right? You don't see crystalline peaks, well-defined crystalline peaks. That is an indication of its amorphousness. Another ash is sugarcane bagasses, right? We are focusing on these materials because they are widely available, and India, for an example, is one of the top producers of sugarcane and rice in the world, right? It comes in top 2. So we generate a lot of this product. So why not to see how can we use it? So again, so far, the application is limited to the cement, right? We are talking about the replacement of cement, and the idea is we are making these materials react with calcium hydroxide, which is coming from the cement hydration and filling the pores and improving the properties, right? So sugarcane bagasse ash is a byproduct again of sugarcane sugar industries, right? It is produced in cogeneration combustion boilers, right? Roughly around more than 60,000 tons of sugarcane bagasse ash is produced in India, right, on daily basis. And mechanical processing has been shown to improve its properties as a pozzolanic material. There's been work done at IIT Madras a few years back by Baruddin et al., where they have clearly shown that when we process sugarcane bagasse, for an example, if you sieve it or grind it, you can significantly improve its properties as a pozzolanic material, and up to 25% replacement you can do, and without any influence or detrimental influence on compressive strength. That's what is shown in this figure. Okay, so we so far know that, okay, we can use these rice husk ash and sugarcane bagasse as cement replacement, right? Significant number of studies exist on this aspect. But often you will notice that there is, as mentioned in earlier lectures also, we always look for consistent properties, right? We always want to work with material which doesn't change its properties, right? Otherwise, our properties will get affected. So for an example, limit on LOI is very important. Loss on ignition, that's an indirect way of measuring residual carbon, right? So you don't want to have a lot of residual carbon, because that will then start affecting the properties, which includes your fresh properties and also later age properties. And typically, when we talk about cement, like concrete, where Portland cement is the main binder, replacement level is usually limited to 25 to 30%, again, depending on physico-chemical characteristics of RHA and SCBA, right? Depending on its characteristics, the replacement level is limited. Now we are talking about, right, we are talking about these waste and we want to utilize these waste. So definitely we have to talk about high volume utilization, right? So we are now switching gears towards high volume waste utilization. How can we do that, right? So for that, we need to characterize these wastes properly, right? What are the physico-chemical characteristics, right? Which includes, for an example, particle size distribution, phase composition, crystalline content, amorphous content. As we know that amorphous content affects the reactivity, or you can say dissolution of these materials. So we need to have a better idea of all these characteristics, right? Before we start thinking of high volume waste utilization. Also, we need to have a very good understanding of this, residual carbon, how much residual carbon we have, and how is it going to impact properties, right? And also, we may have to look at low energy pathways, right? For high volume waste utilization in form of alternative cementitious binders, right? So conventional wisdom is, you have a cement, you start replacing cement, you go to 20% replacement, 30% replacement. But if you go beyond that, it may start hampering the properties. But is there any other way, right? Low energy pathway, which makes sense for the high volume waste utilization, right? Also, suppose you have a waste which has some features which you do not want, right? And how do we take care of that? So with that in mind, I will just share our work on Indian biomass ash. Basically, this is the work we did with paper industry in North India. And just if you look at some numbers, we have roughly 800 paper mills in India. And these paper mills rely on agricultural waste to get energy, right? In that process, they end up generating a lot of ash on daily basis. So we are talking about 10 to 15 tons of ash. And again, this ash has to be landfilled, and there is some cost associated with that. So roughly the cost of landfilling, if you just try to rough calculation, you have to spend significant amount of money, right? Not to say that there are other impacts on environment with the disposal of this ash. So same thing which I shown earlier, you see here, this is the biomass ash generation, right? You see boiler here, because you are using these agricultural waste, we have a lot of ash, boiler ash, we say, right? Now, the problem is this ash contains a lot of residual carbon. We are talking about 20 to 30% of LOI, which is significant, right? And again, it has significant compositional variability. Season to season, there will be significant difference in the characteristics of ash. The question comes, how do we make use of this ash, right? Currently, that's the scenario. It is being landfilled, so there are a lot of concerns with that, right? So idea was, can we do something? Can we use this ash, and rather than directly going for concrete, can we make bricks, right? It could be an alternative to fired clay bricks. And we know that there are some issues with the fired clay brick. The issues are related to topsoil depletion, because you have to use good clay, right? Then the land loses its fertility. And we have to fire these bricks at really high temperatures. So there's air pollution associated with that, right? And significant energy consumption. So these are all the issues with the fired clay bricks. So the idea was, can this ash, right, in edge received state, can be used for bricks, right? So let's look at some of the properties. Again, I will refer to the studies or lectures just before me. You know that now that the amorphous content plays a big role in terms of influencing its reactivity, right? And determining amorphous content is not very easy. You'll have to do a detailed quantitative X-ray diffraction to get the amorphous content. So let's look at these couple of ashes, right? How do we see, if you look at the X-ray diffraction, you see a broad hump, right? Broad hump between I would say 15 to 30 2 theta degrees, right? That is indicative of the amorphous content of ash, right? So that tells us that we have some amorphous content which can be used if we can harness that, right? Just for an example, I'm also showing you here the X-ray diffraction of clay, right? Which doesn't seem to have any amorphous content. Mostly it's a crystalline. So as you will see in later slides, this clay, although was used in making bricks, but acted as just filler rather than being a reactive material, right? So again, the difference between these two ashes in terms of feedstock was, you can see Bindless ash had sugarcane bagasse and also rice husk, 63% sugarcane bagasse and 27% rice husk, right, as a feedstock. And Silverton ash, on the other hand, was primarily based on rice husk, right? So that is going to affect the properties, right? So now I would like to draw your attention to this table, right? So you see here first loss on ignition value, significantly high, right? So 35%, 29 to 35%. That's the range. So we know that these ashes have a lot of residual carbon, and that's going to impact the properties, right? Also, if you determine the amorphous content, you see that amorphous content can range from 85 to 90%. But I will warn you that this amorphous content includes the contribution of unburnt carbon, right? So you have to, if you look at, you have to look at the amorphous content which you need for the reaction. We have to isolate this, the contribution of unburnt carbon. So one way to just look at this difference, right, is look at the X-ray diffraction, right? So on the left, this plot, figure, X-ray diffraction pattern, you see this is a raw biomass ash, right? You see crystalline phases, also amorphous hump, right? And amorphous hump is basically from your siliceous, amorphous silica and residual carbon, right? And what is interesting, like if you look at three different fractions, right? On the second figure, XRD plot, you see when we sieve this ash and get really fine ash, which is less than 45 micron, and then look at the effect of size fraction, you see the hump, right? The shift in hump, right? Shift in hump. So in coarse fraction, right? Hump is centered around 25 degree 2 theta, right? So basically it says that most of the residual carbon is in your coarse fraction, okay? If now look at the X-ray diffraction, the last one, third one, what we see that, suppose we want to dissolve this ash, right? Suppose we dissolve this ash and we see that the residual amorphous hump, right, that stays. So if you look at the red X-ray diffraction pattern, right, there's no change in the XRD pattern. If you look at around 25 degree 2 theta, where the residual carbon is, right? So basically what it says that your total amorphous content is made of these two, and residual carbon is not dissolving, for an example. Nothing is happening, only your reactive siliceous part is taking part in reaction. So that just shows you. So idea is now these ashes are primarily siliceous ashes, right? Rich in silica. If you can use the silica, right? And again, if you can supply some calcium, we would guess that might be formation of calcium silicate hydrate, right? The same hydration product which we see in hydrated Portland cement. So there's some potential in that direction. That was the thinking. So first, let's look how quickly these ashes dissolve, right? So on the left figure, you see comparison between these two ashes, right? So one ash is definitely doing much better, right? In 28 days, you see 70% dissolution, right? And this was measured using ICP, right? you can dissolve this ash in alkaline medium, which was 2 molar sodium hydroxide, and you can track the silica, how much silica is getting released, right? That can also tell you the degree of dissolution. And as I mentioned earlier, as you can also see from X-ray diffraction, you can see that clay was not very reactive, right? 6-7% of reactivity compared to 60-70% of reactivity for the ashes. What is interesting, same dissolution study, what happens when you start adding calcium, right? In this case, this same ash was dissolved in 1 molar sodium hydroxide, but in presence of calcium hydroxide. So you see there's a reduction in the dissolved silicon in solution. Why? Because part of silica is reacting with calcium hydroxide and forming CSH, right? So that way the net dissolved silica in solution is lower in presence of calcium. So we will try to now use this and see how can we develop binder, right? So with the edge received ash, which had this really high carbon content, right? We started with 70% ash content with some clay and 10% lime, right? Lime just for a source of calcium. And we formulated this binder, okay? And 1/2 to 2 molar sodium hydroxide was used, right? We try to lower the concentration because there is always some concern with high alkalinity, but we have shown that even 1/2 molar sodium hydroxide works really well. What was interesting was this binder didn't have to be cured at high temperature. So if you look at these two, one fired clay brick and the brick made using these biomass ash, right? This was just cured at 30 degrees Celsius, right? And the kind of strength we got was enough for the application, right? So this in 7 days, the strength of these binders was more than 7.5 to 8 megapascal, right? Again, our target was brick masonry. You can do some characterizations, right? You can do X-ray diffraction and FTIR to just be sure that what kind of hydration product is forming. Now we know that we can dissolve this silica, right? Amorphous silica, and make it react with calcium hydroxide and form calcium silicate hydrate. So that you see when you do X-ray diffraction, you see peak at around 29 degrees to theta, but the problem with that sometimes is it overlaps with calcite phase. So you have to be sure, and you can do FTIR where you see this band at around 965 wave number, which clearly tells you this is the phase, the CSH phase, calcium silicate hydrate. So we are forming something similar, but obviously the stoichiometry will be different, right? See, the main, the interesting point about CSH is the stoichiometry changes. Basically, we are talking about calcium to silicon ratio. So in this case here, I'm not going in detail, but we are forming CSH, which has low calcium to silicon ratio. Okay, so we have seen now that we can use these as received ashes, right? Without processing, right? And we can develop a binder, right? So in this study, then we thought, okay, what about durability, right? If you talk about the bricks, they have to be outside, they have to be exposed. And what is the effect of environment, right? There are issues with leaching. For an example, if you are using alkaline medium to activate ash, right? How much alkalis will leach out? Will that cause efflorescence? Those were the concerns before, right? So here you see a prototype, right? So we did this prototype and was exposed in environment, right? And after 1 year, there was no issue, no cracking, no efflorescence, right? And we even tested the strength of these bricks, right, from this wall, and all had more than 8 megapascal strength, right? So there was no loss in strength, even though they were exposed for a long time. They are now more than 2 years, but there is no issue. Finally, life cycle assessment test, the study was done to show that these bricks, biomass as bricks, had lower environmental burden, right, than fired clay bricks for obvious reasons. We didn't have to heat the, heat for curing, right? You could just cure this binder at 30 degrees Celsius, right? And also we are using waste. So in comparison, let's look at let's compare fired clay bricks versus biomass ash brick. What I would draw your attention to, the bricks made of biomass ash brick were like roughly 30 to 40% lighter. So imagine like how much impact it can have, right? And thermal conductivity was really low. So if you think from insulation perspective, right? If you think from furnaces, right? High temperature furnaces where you have to provide some bricks, right? So, or even for thermally comfortable housing, right? Where we want some sort of insulation. So these bricks seem to have some potential, right? Strength also can be controlled because, if you test fired clay bricks, you will see that there's a significant variation in the strength, right? Sometimes you will get really bad brick, which will be around 2-3 MPa. Sometimes you may get very good brick. So here we get consistent properties, right? We can control that. So this is my last slide. So basically what's the current work and challenges? We need to map these waste in India, right? We need to know where are these waste and in what is the amount, right? That's also very important. Then it's very important to assess their reactivity, right? It's very important to characterize them well, right? Because there's a significant compositional variability and presence of residual carbon. A lot of times things are not under our control. Obviously we can process these ashes, right? Make these better and then use it. But just to make the solution economical one, we want to use as received ash. For that, we need to have a very good understanding of the properties, physico-chemical properties. And we are looking at low energy pathways, right? For high volume utilization, we are talking about more than 50% volume utilization, right? Then only we'll be able to make use of these wastes which are available widely in India. And eventually, as durability is very important, right? Transport and leaching studies have to be looked at carefully, okay? Before we look at the scaling up of these chemically activated binders. Okay, with that, I would end my talk. Thank you.
Thanks, Piyush. Lot of questions have come up about the different waste. You talked about agriculture waste.
Yeah.
Have you done any work on construction waste or granite slurry waste? Are these things that we should be working on?
Yeah. It's very good question, and we are actually, I'm not yet started working, but these are definitely of interest, and granite waste, marble sludge waste, and there is definitely some potential, but there has to be, we have to do some work on that. But very good question.
Yeah. So, and then question, does waste need activation? Always.
Yeah, so that's again good question. Depends what kind of waste is it. As you would know, some waste may be hydraulic, latent hydraulic. So depending on, that's why we need to have a very good way to characterize these waste, so that we can understand whether they need to be activated or not. Sometimes they may not. So, but we need to know, we need to properly characterize this, then only, or use a rapid screen test, what Pranoy suggested, right? That could be also one starting point.
Okay. Follow-up question. Maybe you can turn on your video, Piyush.
Yeah.
Yeah. So another question following up from that was, can we use the waste as raw feed for OPC manufacturing instead of as an admixture or addition? Can we put it directly into cement manufacturing? Is there any work on that?
That's an interesting proposition, because I can comment on, I'm working on calcium sulfur-aluminate cements, where we are looking at the raw feed for that. So these wastes, which are rich in alumina and silica, we are potentially thinking that we can use these wastes as a raw feed. But to make cement, I don't know if any work has been done in that respect. I can't comment, but there is some potential, but has to be looked at.
Okay. And then there are several questions, both on YouTube and chat, on what would you say is better, the fly ash, the alkali the AAC blocks, the aerated blocks that we have for building, or your waste blocks?
Again, it's a good question. I think for that we'll have to do a detailed study. Actually, what I would say that it all depends on application. What do you want? There's no one solution which fits all. We are looking at tools for specific applications. That's how I look at this. So depending on the climatic condition, depending on the exposure condition, depending on the loading condition, then we have to look what kind of strategy we can devise. So it will be unfair to directly compare these two because each one can be used.
Your impressions on plastic waste. So everybody now is worried about plastic. So the question is about what do we do with plastic waste with respect to concrete?
It's a very important question. As far as my understanding goes, I mean, see, small replacement of plastic may work in terms of getting something, but we are looking at the value addition. We just don't want to put anything in concrete, right? We want to understand whether really it improves the properties. From that perspective, I think there's not much work has been done. I think definitely more work is needed in that direction before we think of using plastic in concrete.
Okay. How about the carbon content or the high LOI that we have? Is that a problem, and should we worry about it or use that as a screening?
Yeah, it's a very good question. So residual carbon usually has issues, right? It tends to absorb a lot of moisture, right? It interacts with your chemical admixture. Suppose you are using it in concrete, but what we have seen, depending on what you want, right? So bricks, for an example, although these bricks had high absorption, I would say up to 20%. That's the limit. Even it was not very high. We could get it down to 20%, which was manageable. Then we could use these bricks, in place of fired clay bricks. So obviously, yeah, that will affect some properties, but we didn't see its impact on strength per se, right? That was from our limited work. But we were with the proper mix design, we were able to reduce the water absorption, because that's one of the things when for bricks, right? If you want to use bricks, you have to meet the strength criterion, and also you have to meet other criteria. So this is one of those that the water absorption has to be low. Yeah, there is some issue, but that can be tackled. That's what I'm trying to say.
Okay. Any thing that we should be cautious about, or things that we should be careful about in terms of using waste in concrete or to make bricks?
Yeah, so again, it's a very important question. Any waste, right? We have to look at the value addition. For that, we have to properly characterize it. Properly characterize it means we need to know what's its degree of amorphousness, right? How much amorphous content does it have? What else does it have, right? Which can potentially hamper its properties. So we need to have very good understanding. Then only we should devise a plan to use it, right? Depending, do we want really high volume utilization of the waste in as received condition? See, sometimes economics may work out, right? You may able to process it, then definitely you can make it better. You can make it as good as good materials which we use as a cement replacement, but a lot of times that may not be feasible. For that we have to look at other alternative ways. So it all depends on the characterization of this material. That's why it's very important to properly characterize it and assess the reactivity.
Okay, so again, a lot of interest, Piyush. I think you could look at the questions on the chat and YouTube also. A lot of people are interested, and especially young people looking at research topics. Always we find that students want to put new things into concrete and find out what happens. So I'm sure now that a lot of motivation will be there to put waste in concrete. So
Thank you.
thank you, Piyush.